Today we are going to do lecture 5 of chapter 1, which will be on section 1.4, measures of variability. So these are the objectives outlined on page 21 of your study guide. So after this lecture, you should be able to compare dot plots in terms of measures of center and variability, calculate and interpret numerical measures of variability, calculate and interpret the range of a data set, show that the sum of deviations from the mean is 0, define the sample variance and sample standard deviation, differentiate between a sample variance and a sample population, derive a computing formula for the sample variation, calculate the sample variation, calculate and interpret the sample standard deviation, show how the sample variance is influenced, calculate the interquartile range, calculate and interpret a 5-number summary for the dataset, draw a box plot, define and identify an outlier in a box plot, use a comparative stem and leaf display to construct comparative box plots, and interpret comparative box plots. So just a quick reminder, we are busy with the Descriptive Statistics branch. In Descriptive Statistics, there's graphical measures and numerical summary measures. This week, we are busy with the numerical summary measures. In the numerical summary measures, there's 2 groups, the measures of location and the measures of variability. The previous lecture, we looked at the measures of location, which included the mean and the median, the quartiles and percentiles, the trimmed mean, etc. So today we are looking at the measures of variability, where we are interested in how far the data is spread out. So you can see this little graph on page 32 of your textbook. So these are 3 different data sets that has the exact same measure of center. But all 3 of these have different measures of variability. The first one at the top has the largest amount of variability because the data is spread out over the entire range. This third one has the least measure of least variability in the data. Okay, because the data is more compact. And the second one is just in between. Okay, because the data in the center is quite close to each other, but it does have these outliers. So the first measure of variability that we can look at is the range. So the range is just simply difference between the smallest and the largest value. Then one of our primary measures of variability will involve something that we call deviations from the mean. That means that you're subtracting the sample mean from each of the sample observations. But there is a problem with this. That is that the sum of the deviations, if you work that out by taking in the sum, you get this. If you simplify the mean so that it is in the sum of the mean, so that it's n mean, because the mean is just a constant, then you get this equation over here. And you can simplify this even further to be the sum of the observations divided by n. And then this whole thing simplifies to the sum of the observations. And the sum of the observations minus the sum of the observations is 0. So the sum of the deviations from the mean is just 0. So can we make a plan? So we want to change the deviations to non-negative quantities. So the first plan that we can make is the average absolute deviation. But the absolute value operation can lead to a number of theoretical difficulties. Therefore, let's rather consider the squared deviations. And this seems to be a solution. But for several reasons, we rather divide the sum of the deviations by n minus 1 rather than n. Okay. So then on page 33, we define the sample variance to be the sum of the deviations divided by n minus 1. And then the sample standard deviation is just the square root of the variance. And then the unit for the standard deviation is the same as the unit for each of the observations. Okay. So let us look at an example of how to calculate the sample variance. So this is example 1.14 on page 34 of your textbook. So we have these data observations, okay? And we took the sum of this and that resulted into 365.9. Then the first step will be to calculate the deviations from the mean. But before doing that, we need to calculate the mean, which is the sum divided by our sample size. And that gives us 33.26. Then we take this sample mean and we subtract it from each of these observations. And that is what we get. So then we can just check the sum to see if it's close to 0. And yes, it is close to 0. The reason why it's not 0 is because of rounding errors. Then we take the square of each of these deviations from the mean. And that is what we get. All positive. Then if we sum this together, we get the sum of the deviations. And then to calculate the variance, we take the sum of the standard deviations and we divide that by n minus 1, n being the sample size. And this is the variation that we obtain. And this is our standard deviation if we square root the sample variance. It is important to note that to avoid rounding errors, you should only round your final answer. Do not round in between. Keep as many decimal points as you can. The next thing that we're going to look at is the population variance. So, the population variance we denote by sigma square. So, sigma is the Greek letter. Okay, so this is the lowercase letter for sigma. Okay. Then the population standard deviation is just the square root of this. So it's just the sigma without the square. So then the population variance is defined as the sum of all the observations minus your population mean divided by capital letter N. Okay, so it is the average of all square deviations from the population mean. So we will, as we did with the sample mean, we define the sample variance so that we can make inferences about the population variance. Okay. I just want to remind you that this is the formula for the sample variance. Okay. So if we knew the population mean, we could have used the population mean here instead of the sample mean. Okay. But the population mean is almost never known. So the sum of the squared deviations about the sample mean must be used. But the xi's tend to be closer to the sample mean than the population mean. And remember earlier I said that we divide by n minus 1 instead of n for some reasons. So this is the reason, because the observations tend to be closer to the sample mean than the population mean. So to compensate for this difference, we divide by n minus 1 rather than n. So if we used n instead of n minus 1, then we would have underestimated the variance. Okay. Then as you would have seen from the example that we did a few slides earlier, to calculate the variance is quite a tedious task. So we construct a computing formula to be able to calculate the variance much easier and to guard against the effects of rounding. Okay. So this is the computing formula that we are going to use. So it is just another way of writing the sum of the square deviations. Okay. It's important that you know how to prove this equation. Okay. I will talk you through the proof that is on page 35 of your textbook, but it is advised that you go out and write it out for yourself. Okay. Make more steps as long as you get to the right answer. Okay. So the first step is to prove these, or to define these two mathematical expressions. So the first one is just the mean, which is the sum of the observations divided by n. And then n, sample mean squared. That deduces by, if you substitute the sample mean in, then it deduces to the sum of the observations squared divided by n. Okay. Then you start by saying the sum of the deviations about the sample mean squared. So when multiplying out these two brackets, this is what you get. Okay. Then you take in the sum to each of the terms, and this is what you get. So here, what they did is to take out the constants, because the 2 and the x bar are constants in this case. Okay. So then this deduces to the sum of the observations deduces to n times the sample mean that you can get from this result. And the sum of sample mean squared is just n times sample mean squared, because this is again a constant. Then it is 2 times n sample mean squared plus n sample mean squared. So that is minus n sample mean squared. And this term stays the same. Okay. And then at the top, we defined this quantity to be the sum of the observations squared divided by n. And that's what we substitute in. And then that is my computing formula. And it is very important that you know this proof. Okay. So then, on the bottom of page 36, we have this proposition. Okay. So it says that you have a sample x1 up until xn. And you have a constant c. So if you add the constant to each of the terms in this sample, then your new sample y1 up until yn will have the same variance as your sample of x. Okay, and that is because my data just shifted up. The spread stayed the same. Okay, so in this case, my mean, my measure of location, will change because that is what changed, my location of my data. Okay. If we multiply the constant with each observation in the sample of x's, then my new sample of y will have a sample variance that is a little bit bigger or smaller instead of, it depends on this constant. So the sample variance of the x multiplied with the constant squared, that will be my sample variance squared. Okay, that is because the data is multiplied, so actually the spread of the data changed. Next, we're going to have a look at box plots. So box plots can be used to define some of the most prominent features in a data set. Okay. So the first feature that can be displayed by a box plot is the center. That is the median. The second is the spread of the data. And then the extent and the nature of any departure from symmetry. And then the identification of outliers. Because of the mean and the sample standard deviation, that is quite sensitive to the outliers. The box plot is based on measures that are more resistant to the outliers, which is the median and the fourth spread. Okay, so what is the fourth spread? That is the difference between the upper fourth and the lower fourth. Now, what is the upper fourth and the lower fourth? The upper fourth is basically my third quartile, and the lower fourth is my first quartile. So let us just read through the definition. So you order the n observations from smallest to largest and separate the smallest half from the largest half. The median is included in both halves if n is odd. And then the lower fourth is the median of the smallest half, and the upper fourth is the median of the largest half. Remember, in the previous lecture where we handled the measures of location, we had a look at the quartiles, and I explained that the quartiles split the data into 4 equal parts. So this is exactly what we are doing here, just in other words. So this lower fourth is equivalent to my first quartile. Remember, the median is my second quartile, and the upper fourth is my third quartile. Okay, so this fourth spread is also known as the interquartile range because it's the difference between the third quartile and the second quartile. Then my box and whisker plot is based on the 5-number summary, which is the smallest value, the minimum, the first quartile, the median, the third quartile, and then the maximum value. Okay, the steps to draw a box and whisker plot. So you start by drawing a horizontal measurement scale. Then you place a rectangle above this axis. So this rectangle, the left edge is the lower fourth, the right edge is the upper fourth. And then you draw a vertical line where you have the median. Okay, and then you draw the whiskers to the maximum and the minimum. So let us look at an example on page 37. It's example 1.6. Okay, so here's your data that you have ordered from the smallest to the largest value. Okay, so here, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19 values. Okay, so 90, that's my median, my x tilde. So then the lower fourth is the median of the smallest half. Okay, so then in this part, there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 values. So then I take, so it's the middle values, the middle value of these 10 values. So I take 1, 2, 3, 4, 5, and 1, 2, 3, 4, 5. So it's the average between 70 and 75 because it's exactly here in the middle. So that's 72.5. The upper fourth is the middle value of the larger values. Okay, so there should also be 10 values. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So it is 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So it is the average between these two middle values because it's exactly there in the middle. So that's 96.5. Then your smallest xi is your minimum, 40, and your largest xi, 125. Okay. And then that is your resulting box plot. So we have the horizontal scale, which is important that it's on scale. Then there's your rectangle with the left edge on the lower fourth, 72.5. The upper fourth on the right edge. Your median is this line over here in the middle of the rectangle. And the whiskers, these lines are drawn up until the minimum and the maximum. Okay. Then your box plots that show outliers. So a box plot can be used to indicate explicitly the presence of outliers. Now, how do we say that this observation is an outlier or not an outlier? So we say any observation further than 1.5 times the fourth spread or the interquartile range from the closest fourth is an outlier. I will show I will have more detail now. And then an outlier is extreme if it's more than 3 fourth spreads from the nearest fourth and is a mild outlier otherwise. So let's see what that means. So we say we have these bounds for the mild outliers. So it's the lower fourth minus 1.5 fourth spread or the upper fourth plus 1.5 fourth spread. Okay, so any value smaller than this value is called an outlier. mild outlier. Any value larger than this value is called a mild outlier. So those are the bounds. So anything outside those bounds are outliers. Okay. Then lower fourth minus 3/4 squared. Everything lower than this is called an extreme outlier. And everything larger than the upper fourth plus 3/4 spread is also an extreme outlier. So in a box plot, the mild outlier is defined with indicated with a closed circle, and the extreme outlier is indicated with an open circle. Okay. In the case of a box plot that shows outliers, the whiskers only go up until these values. Okay, it's either this value or the maximum value. It depends on which one is smaller. Okay, if the maximum value is smaller than these values, then there's no outliers on the upper side of the data. The same with the minimum. If these values are smaller than the minimum, then there's no outliers on the lower side of the data set. Okay. The last thing that you also need to do for this section is comparative box plots. Okay. So these are an easy way to reveal similarities and differences between two data sets. Okay. So as we did with the stem and leaf diagram that was side by side, we also now have box plots that's side by side. Okay. It's easier to see the spread of the difference in the spread of the data if you have the two box plots directly next to each other. Okay. You should be able to go from a stem and leaf diagram to a box plot. So the side-by-side stem and leaf display to a comparative box plot. Okay, there's an example of that on page 40, which you can go over in your own time.